That's good. So we're talking about images. We've been talking about images, and one of the things that you sometimes hear about a lot when it comes to images involves what is known as a Fourier transform and a convolution. I don't know if you guys have ever heard of that in other contexts. But what I want to do is sort of step back and kind of say, all right, an image is nothing more than a signal, but in two dimensions. So the other type of signal that most people are familiar with, but don't necessarily understand, or don't, you really don't need to understand it. You just know, you can sense it, is sound. And what I'm going to do now is do a couple of demos with regard to how sound is, one, generated, and the other one is how it's analyzed. So the best way to do that is to actually use a, oops. Okay. Oh, on. So much for my checklist. Is to talk about the sound. And the way I want you to think about sound is it's very similar to an image, only it's in dimension of time. So I brought a couple of come on, a little bit of a demo here. And let me just, I didn't know if they had. So what I'll be using is a open source tool called Audacity. Some of you may have heard about it. It's basically just a audio processing tool. And what the basic thing that you can do is do recordings, record a sound. And what we're going to do is a little more than that. In fact, looks like it's on here. Hopefully hopefully the speaker, the microphones will pick it up. But essentially, if you hit this and I start talking, it's not picking up microphone. Oh, I know why, because it's being used by it's being used by Hangouts. And it's okay because I do have a backup, which is my laptop. So I'm just gonna. I was doing a little bit of testing, but I'll just quit out of Audacity and start fresh. Yeah. So we'll do a little bit of show and tell here. I was just doing some testing to make sure that everything will be working. So I'm going to start at fresh Audacity. And so, like I was saying, you can just use it as if you were just recording. So if I just hit the record button, you hopefully will start seeing my voice over there, and you can see that you're actually getting some sort of a signal. So in terms of images, you can think of the height of all this, of all the sound waves, as being some form of brightness. So brightness associated with an image. Uh, but in order to understand some of the concepts that we're going to talk about in terms of Fourier transforms and signal processing, what I'm going to do is I'm going to make this a little more simpler. So what I've done is I've actually brought an instrument here, little ukulele, and just to show you some of the concepts associated with musical instruments, and hopefully what you'll see with some of the sound processing that we talk about will translate over to images. So let's create a new project here, and we'll start a recording. And I'm just going to strum one. Okay, stop that. And signals are actually represented can be broken down into sine waves. So you can have multiple sine waves, and depending on how those sine waves are added and shifted, any sound that gets generated can actually be decomposed into sine waves, just pure sine waves, all right? And the way to think about that is that you can keep adding different types of sine waves to form a very complex signal. So let me just pop up that concept in one of the slides that I have here. And let me see if I have that. Yep. And I won't go through the math, but one thing you want to realize is that if I were to make what's known as a square wave, it is possible to just take one sine wave of some frequency, another sine wave of higher frequency, and another sine wave of higher frequency. And what you can do is you can modulate this, use different amplitudes. So the amplitude is basically what the distance is between the peaks. And the other parameter that you have is the phase. So you can shift these things back and forth. And what actually Fourier the Fourier theory says is that any signal that I have that I can represent can actually be represented by a bunch of sine waves. Right? Each of the sine waves will have different amplitudes, but also different phases. So what you can actually do there is to decompose a signal like this into what's known as a spectrum. Right? And what is that? Well, the spectrum basically is a decomposition of the signal into the different sine wave components. Some of you have probably, as I mentioned before, you probably have seen a graphic equalizer on a sound system. You kind of see it shows you the power spectrum, and you can actually do filtering on that. So what does that mean? Well, there's actually a spectrum. So what does that mean? Well, that means that it tells you the amount of each frequency of each sine wave that we have up there. So this is a very complicated signal because it shows that there's a lot of components associated with the different frequencies. So this is sound, so it goes from 22 hertz all the way up to about 22 kilohertz. So that's the range of what the human audio system can detect. Now, this is a very complicated. Oops, I'm sorry, I forgot to. Realize that. So let me repeat that so you can see what the, and you can try this on your own also. You can download Audacity, you can do some sound, you can record some sounds, and the analysis tool that we use here is what's known as a spectrum plot. So what this is telling you is that this signal here has all these different components of sine waves. So it tells you that there's a high value associated with all those different types of frequencies. And I'll actually just show this to you and actually create a much simpler signal that you can then sort of understand what I'm trying to convey here. So there's a couple of filterings that you can do to sound waves. There's something called a low pass filter. So let's actually, hopefully you can hear this. So that's what we recorded. You can create a process of actually filtering this by doing what's known as a low pass filter. What is a low pass filter? Low pass filter basically says I'm going to remove any any components beyond a certain frequency. So what you're going to do is you're going to remove certain sounds, and I want you to just listen to this again. Oh, start here. So you can sort of hear that it has a lot of forget the proper term, but quality associated with the sound. If I actually then start removing some of these frequencies through a process called filtering, actually look at the this is what's known as doing a low pass filtering. What does that mean? What that simply means is that I'm going to clip out a bunch of frequencies, higher frequencies, that in order to change the quality of the sound. And a lot of these other things, a lot of these other parameters here, don't worry about it. The three things that I want you to get out of this is low pass filter, not the notch filter, we'll do that later. Low pass filter, all right. Oh, select the audio. So I'm going to select the audio that we want to process. And now I'm going to apply low pass filter. So what I'm going to do is, by this process, is I'm going to essentially remove a whole bunch of these frequencies. So let's make this a little higher. 100 is fairly low. Do 1,000. And if we actually look at the spectrum here, if I say replot, we're going to replot it. Anybody see any change associated with that? No, not too much. Well, let's see what it sounds like. All right. So what you should be hearing is a little more, a little more muted. So let's actually increase that filtration. Let's actually filter that out a little more. That's probably why I had 100 there. I was testing that at 100. If we plot this, it should, yeah, it took away a lot of those frequencies. You still have the basic signal, And now if we actually play this, it doesn't have all those high frequencies. So what you've done is you've filtered out a lot of the higher frequencies, and we'll see that in an image example. But this is typically what people do with signals. So if now let's say we want to do what's known as a high pass filter. In other words, we get rid of the lower frequencies and allow the higher frequencies to come through. Let's undo this. That's where we are. This time, let's apply a high pass filter. And if this isn't making sense right now, don't worry. I think when we actually talk about the image examples, you'll start understanding a little more. This is some of the concepts that I was introduced to before learning about this in imaging. So let's go ahead and do an effect here. And the other one is high pass filter. Actually, before we continue with that, let's replot this. So that's basically the original signal we had. Now we're going to filter out through a high pass filter, which means just give me everything above 10,000 hertz. So let's see what that looks like. We replot that. And it's kind of hard to see, but this actually removes some of the lower values and kept some of the other ones. And when we talk about the other type of filtering, this should probably make more sense. So let's play that. So it's very tinny. You don't have the bass associated with it. Because what high pass filtering has done is remove some of those lower frequencies. And if you think about a bass of music, it's usually low frequency information. What this filtration did of high pass filtering is that it got rid of that sort of foundation and essentially kept just a high frequency, all the changes in a signal, the extreme changes that occur. So that's a form of filtering that we'll actually see in images. I'm just trying to present it to you in terms of sound. So what we're going to do next is actually look at a more specific type of sound, a much cleaner type of sound. I probably should have started with that first, but I wanted to sort of give that. So any questions with this so far? This is the time to ask why do we care about this?
Is that information enough to recreate the sound, like by just
Yes, correct. Yeah, if you have a Fourier transform, of a signal. Now this is just there's a lot more information in there that it's not being displayed. One of those is called the phase information. Remember when I said some of these sine waves you can move back and forth? Mm-hmm. That's what's known as phase information. Okay. So if you actually have the Fourier transform of an image, the full Fourier transform, both the magnitude, how much signal, and the phase, how do I shift this? You can actually do that. In fact, some of the examples I'll show on the image part, that's actually what you do. What you would do is you would bring it into Fourier space. So this signal is in, you can think of this signal as being in time space. This is Fourier space. So what you've done is you've taken that signal and decomposed it into a bunch of sine waves. And those sine waves, you modulate phase and the magnitude, the amplitude. And it is possible to basically reconstruct this information from this information.
Along with the phase information.
Exactly. And what's interesting is that this in the Fourier transform space, it now becomes a little easier to do the filtration. You can filter out the different components of that. The concept that is associated with this filtration concept in the time space is known as convolution. Convolution is simply taking a little kernel and just moving it across a signal, and you can either do averages or you can do other subtractions. We'll talk about that later, but you are correct. The Fourier transform will have all the information that you can do to reconstruct any signal. So it's just that in this space, it's much easier to work with it. So let's do a simpler case. So I'll do another recording, and what I have now is an app called the tone generator. That's basically an audio tool, and what we're going to do is just create a sine wave of a specific frequency. So if I play this now, I'm saying, what? I'm just wondering if it hooked up to a Bluetooth. Ooh, yeah.
I turned my headphones off.
Oh. Oh, no, it's probably good. So right now, this is 5,000, about 5,000 is the frequency that we're doing. So I'm going to just record it now. Very annoying. And that's the signal that we're getting. I'm going to stop that. And stop this so that we don't go crazy. But this area is when I started talking. So what we'll do is we'll filter out this, we'll do this area. And keep in mind that there's also background noise with that. So I had that set at 5740 hertz. So what this means now is if I take the Fourier transform of this signal, we should get a high signal at 5740 hertz. So let's actually do that now. And just realize I probably should have started with that just to illustrate that fact. And there you go. You're seeing this should be about 5.7. And yep, so you can see 5739. So why is it high there? Because we created a signal that's a pure sine wave, okay, at that frequency. If I now create another one, in fact, let's do that to convince ourselves that that's actually working. Somebody pick a frequency. 100? Okay, that's actually a good one. Let's try that one and see how that sounds. So, let's see if I can actually yeah, let's do 200. It's very quiet, so I don't think I can make it any. Well, let's try it anyway. See if that applies it. It's very quiet, unfortunately. So, project. The other sounds might actually go over. Let's see. But the sounds great. There's something else. So if you think about it, there's actually fans that you're hearing. So that may actually be masking that other sound. So This one, let's see what the, oh, that could be it. Yeah. That could, 200, no, let's see. One, that one, this one here. The type in, I'll type in 190. Let's try another one. Let's do, another one. Let's do that. Yeah, this one's very good. This one's a doing 9,000 right now. We're going to record this. And what I'm going to demonstrate is the process of filtering out this particular signal. Let's go ahead and do another one. Okay, like that. 9,000. So I had set at 9,000. Now I'll select the region, do the Fourier transform, spectrum. So we should see a peak at about 9,000. There it is, that peak, because we're generating just a sine wave of that, for that signal. You see other stuff here because we have background noise. So actually the fan, if the microphone actually picks up that fan noise and all other background, you do get that information, but you'll notice that most of the power is in that particular spectrum of 9,000. Now this is where Fourier transform comes in very handy in terms of filtration. We talked about filtering low pass. In other words, let everything up for a dip above a certain frequency, you cut it out. High pass means something below a certain frequency, we cut it out. But the interesting thing with this is that you can also do what's known as notch filtering. In other words, suppose I have this signal, this 9,000 kilohertz sine wave, and I want to get rid of that. It is possible to do that. So we'll actually demonstrate that right now. And based on what we've selected here, I'm going to do a effect. And then I'm going to do what's known as notch filtering. And what notch filtering simply says is that I want you to target a particular frequency, and around that frequency, I want you to zero out all that information. So do 9,000 here. That's what I was aiming for. And this value here just tells you how wide that filter is going to be. So let's actually see what happens here. If I say OK, you can see that it altered the signal. If we actually replot that, you'll notice I don't know why I kept that, but it actually filtered out a lot of that information around 9,000. That the signal that we're seeing here may be from something else in the background. So typically, if you wanted to do this perfectly, you would go into one of those sound booths and play and basically do the recording so that you don't get spurious information that's showing up here. So how does this sound now? Well, let's play that for this particular section. You don't really hear anything. But if we actually expand this to kind of show you before and after, what I've done here is I've selected the area that we filtered and the other one that we didn't filter. And now I'm actually going to display it, and you'll see what happens when we actually filter out that sound, You heard it. Okay, this is bothering you a lot. Yeah, yeah. Okay, I won't put it on the looping then. But this is actually what you do. You can filter that. This is what Fourier transform filtering will allow you to do. So does everybody sort of get the concept of this? So in terms of EEGs, this is the kind of stuff that you'll be doing. Sometimes you'll get an EEG that's very noisy. You may want to do what's known as low pass filtering. So sometimes you'll get noise out in these some spurious noise out in this region, out here. Some sound noises. So if there's like a pops and hiss that you may get, you may want to just do what's the low pass filtering. In other words, any of the pops are high frequencies. Anything that has a big change is represented by high frequencies. So if you filter out high frequencies, you'll get rid of those pops. Not perfectly, but at least it'll lower that information, that signal, to the point where it's probably not as noticeable. And what you're seeing here is one of the tricks that people do in terms of sound compression. MP3s take advantage of the fact that you can't hear anything beyond a certain frequency. And even though you can record it with a machine, people can't hear it, so you might as well throw that stuff away. So you've had some form of a lossy compression. Some people claim that they can actually hear beyond that, but I doubt it. And as you get older, also, the frequencies that you play, in fact, I don't know, a little demo here. So it's similar to the little demo that we had with the Lena image quality compression. I actually did this with my kids, and they beat me as far as. So I'm going to adjust this now. I don't hear it. Do you guys hear it? Still hear it? Yeah, I can't hear it. At about 11,000, I barely hear it. Oh, it sounds like it's hitting you. So it sounds like you have a different sensitivity than she does. Can you still hear it? Still? I can't hear anything. So it's surprising. So anyway, because everybody has different different makeup of your skull and everything. You might be able to hear that. I can't hear it. But in some respects, the same thing happens with images. Some people have very good acuity on looking at an image, and they can see things other people can't. So how does this translate to images? And that's where I kind of wanted people to get the comfortable concept of signals in the 3D space. And let's actually move now to this, as I've mentioned before. And I didn't go through all the math. I just wanted to go over the concepts with that. So if you think of this as an image, if I draw a line across this, right, and I plotted the brightness, okay, that'll be a sine wave. Same with this, with a different frequency. I plot that. I draw a line across here, plot out the gray values. That'll be this. So what you're seeing here is that you're essentially mimicking what we did with sounds. We did this in an image domain, right? And because images are essentially two-dimensional signals, what you have is this component where you actually have to start measuring all these signals in different directions. This is an example where you have a sinusoidal signal going in one direction and another sinusoidal image going in another direction, and basically you combine them to come up with that kind of pattern. So this just sort of illustrates the fact that you can do the same thing that you did with sound in much the same way that you can do with images. So so the concept of Fourier transform comes from that, and we talked about how that is an analog to the Audacity demo that I presented to you. And this is what people will typically do with sound. You'll have a little what's known as an equalizer, right? So if I were to create a low pass filter, I would probably either level this out and then bring this all down. That would be a low pass filter, because what you're saying is that I'm going to let all of the low frequencies in. Or you can have a high pass filter in which you would bring this all down and then let the high frequencies in. This is sort of like a notch filter, because not quite a notch filter. A notch filter would be, you keep everything going except for one of them. You drop it down, kind of similar to what we did. But most cases, you want to maintain the quality of the sound, so you kind of play with this frequency. So this is what's known as the equalizing the frequencies. A signals, echocardiograms. Some people can actually start analyzing echocardiograms, EEGs, stock market, right? How the stock market jumps up and down. People will try to do time series analysis, similar to what we do with sound. People will actually observe different phenomenon based on how it changes as a function of time, and make some statements associated with that. So as far as images is concerned, we did that. So if I have an image that looks like this, and I take a Fourier transform of it, that's a Fourier transform right there. Not very interesting, but what this represents again is the in frequency space. This is a frequency at a given a sine wave at a specific frequency. This is the middle one. Is think of that as zero frequency. So that center dot there stands for basically just what they call a DC component. It's sort of like a baseline level, and then as you go away from the middle, you get two spikes. One is for the positive sine wave and negative sine wave. They're both the same frequencies. It's just they have different signs associated with that. Okay. So we talked about low pass filtering from the audio perspective, but what we can do here now is to actually do the same thing with images. So this is Lena, and there are actually several types of algorithms that will allow you to convert this Lena image into a Fourier transform. So think of that as all the frequencies of this image. And what we're doing now is we're creating a low pass filter. So what you're doing is you're basically taking the Fourier transform, multiplying it against this mask. So this is anything that's in the white region gets passed through. Anything that's in the black is filtered out, very much similar to what we did with the sound demonstration. And what you'll see is that when this is Fourier space, we do a back transform, kind of like what you asked. Do you have all the information to go back? Yes, you do. I take Lena, do a Fourier transform, convert the frequency space, and I have this information, and I go back transform, you should get the same image. What we're doing in the Fourier domain is we're filtering it out. And what you're seeing here now is you can see that there's a lot of detail that's been lost, because the high frequency detail, a lot of the information in the feathers in her hat is basically in the higher frequencies, right? So a lot of this area here would represent any
regions in the image where there's a big change. There's a big change in the signal. So and that's what's happening here. If this filtration removes even more frequencies, it gets blurrier because you've taken a lot of information out that is represented by the high frequencies. Right? So if you do this in Audacity, it's it's similar to if you put a low enough filter in this low pass filter in a sound, it'll sound very very muted. It's like it sounds like as if you're talking in a tin can or something, because you've lost all that high frequency information, and that's what's happening in this scenario. So the alternative is high pass filtering. And what we've done now is take that same frequency representation, only this time what we've done is we've blocked out the low frequency. So anything from the center out, okay, you can think of this starting at the no frequency and then going out to higher frequencies. So in this case, we've kept the high frequencies and then back transform. What you have here is basically all the edges, because all the edges have the greatest change. And that's actually a form of an edge detection. When somebody says, I'm doing a high pass filter on an image, what they're basically doing is they're detecting all the edges. So that's so it's sort of equivalent in that regard. And as you can see here, it's not as pronounced here, but we're actually, the more you filter out the lower frequencies, the more the edges will pop out. Any questions with that example? So, and all this stuff that I've shown you, you can do that in ImageMagick. Right? You can actually, there's a transform, there's a Fourier transform in ImageMagick to go from here to here. You have to create this yourself, but that's usually fairly straightforward with trying to think if I've done that in ImageMagick before. They might actually have a function that says create a circle, a filter, and you can just do the multiplication. You can also do that in ImageMagick. So notch filtering, similar to what we did in sound. Okay, we played a given frequency sine wave, and then we wanted to remove that. We did the notch filtering. Well, this is a situation where you have an image. What sometimes happens is that your system has what's known as some noise, some periodic noise. This is what's known as periodic noise. If your electronics aren't well shielded, okay, you'll get some noise. So think about AC, power, 60 hertz. Right? So sometimes what you will see if you've got the instrumentation is you'll see that 60 hertz signal being manifested in different ways. Right? This is an example where you have some periodic noise, and when you actually take the Fourier transform of that, it pops up. You can actually see that periodic noise that is in your image. And what you sometimes want to do is like, yeah, I want to get rid of that, or at least you don't typically get rid of it because there's always some underlying amount that you can't really filter out properly. So just be aware that you can't eliminate it. You can probably mitigate it. And what we're doing here now is we're going to take that process. It's the same process that we did before, but this time we target the different frequencies associated with that. And in this case, we create a mask notch filter, remove those sine waves, and then basically back transform. And you can still look at this and see that there's a little bit of of the periodic noise, but it's been mitigated. So these are the things that you would do in terms of the Fourier space. This is something that you can do easily in the Fourier space. So very powerful technique. Sometimes people have a hard time trying to understand what it really means, and that's kind of why I demoed the sound example, because that sort of gives you a sense of what's actually going on with signals. So this concept, any signal, this is what the electrical engineers do a lot. Is trying to take signals and somehow process it to massage it into a much better quality data. This is sort of a cool example that shows you how Fourier transforms can work. Any questions with that? So, go ahead.
I'm sure, like in practice, if you're doing this as in the industry kind of level, you can get a lot really specific with your filtering, right?
Correct. Yes. Yeah. It's sometimes there's a lot of trial and error and being ad hoc about it. So some of the things, sometimes it depends. A lot of the people who've done this are the folks from JPL, and so they would send out from the probes. They come back. There's so much noise that they have their periodic noise that they do these kinds of games to try to mitigate those sources of noise. So this is periodic noise. There's also just random noise, and we'll talk about that I think next week about how you deal with random noise. So when you start dealing with images and signals, the two components that always comes up no matter what you do is signal. Signal is basically what you're after, but every system is not perfect, so you will have noise. So you have to somehow either characterize that noise so you can remove it, or characterize it so you can mitigate it. You can never really remove it. So it's a term that you often hear is signal to noise ratio. We'll talk about that next week, but that is another component of images, and not just images, but also sound. Okay, signal to noise ratio. If you have a system that has a signal to noise ratio of 1, you're not going to be able to do much, because what that's telling you is that the signal and the noise are more or less equivalent, which means that you really can't distinguish between the two. So signal to noise, the higher the signal is to the noise, the more information you can generate. So that's something to keep in mind. Signal to noise, and we'll talk about that next week. Yes?
So if your image was just like a red block, would that mean the spectrum is just like one white dot in the center?
One block. Yeah, so if it's just a block, that's a good question. So you can actually, the reason for that is that what Fourier transforms basically assume is that you have what's known as infinite extent. So because of the fact that you actually chop it, will introduce high frequencies. So in theory, these signals are infinite. Sine waves are infinite. Okay. And I think what you're asking is it probably should show up as a single dot in the middle, and I suspect that it may not, but it also may, because what sometimes happens is that if you chop an image, have that high frequency change, that introduces artifacts, high frequency artifacts.
No, I'm sorry. So yeah, my question was the most original, like just the simplest image possible. What the spectrum for that looks like.
Yeah. So that it would be DC.
Single part of a sine wave.
Yeah.
Like,
well,
actually,
it won't be a sine wave. It would just be what's known as the DC component. It's like there's no change. So that would be like the center part. That center part represents that level where there is no frequency associated with it. Does that make sense?
Yes, that does.
So there's also another concept that I sort of want people to understand. So we talk about sine waves a lot, and there's this concept that you need to understand when it comes to the images and signals in general called sampling theory, right? And so basically what sampling theory says is that in order for me to properly observe and reproduce a signal, I have to observe it at twice the frequency. So what happens if you don't? Well, I brought the little, hopefully I got everything set up here. Oh, no batteries. Fine. Don't brought batteries. And this is sort of a really very visual example of what it means to alias. So aliasing is a term that you'll hear a lot with imaging. And what that simply means is that you're not sampling the signal often enough. And because you don't sample it often enough, you will get artifacts associated with a particular signal. And this is sort of a demo that I like to give because it illustrates a process. This works. You can think of this fan as it moves around spinning as creating a signal, a sine wave. So it's spinning at some certain frequency. And if with a strobe light, you can think of the strobe light as essentially not having any power.
You guys may have to move closer to me to bring a.
There's a signal there going on there. Now, if I'm going to use the strobe light basically to sample the that phenomenon. So this is where aliasing happens. If I alias it to the point where I'm only observing it at a given certain frequency, I can make that thing stop.
It's matched up.
It's matched up, exactly. And this is why sampling theory is very important, because suppose I was trying to characterize the signal, right? And I happen to sample it at a certain frequency where it's always on the same location, okay? You basically will come up with the wrong information, right? Another analog I give is like, suppose you're a space alien and you wanted to measure the tide, but you always came back at the same time of the day. Okay. Your information would say, oh, the tide's always at this level because that's what I always observe it. So that's a form of aliasing, because what you're doing is you're extracting incorrect information from what's actually happening in a given signal.
So it's like the light is hitting it every time it passes.
That's right. You're basically think of it every time the flash goes, you're taking a sample. And you can also come up with different what are known as sampling harmonics, where all of a sudden now you can come up with an incorrect conclusion that says, oh yeah, there's actually 5 of them. So there's, you can have these what are known as beat frequencies. So these are artifacts that you have to worry about, because if you're not sampling something properly, you can come up with these weird representations of the signal. So if you hear about the word aliasing, this should be the thing that pops into your head. It's like, yeah, if I alias, and another example of where you see this is in movies. Sometimes you can actually look at the wagon wheel as they spin, and then at a certain point, you start to look like they're going backwards, right? That's because the sampling of the film as it's exposing it is not happening frequently enough. So that's why you hear a lot of people, oh, I want the 120 hertz TV, because what you're doing there is you're allowing more signal to be reproduced a lot more with higher fidelity. So let's see if we can, yeah. So I don't know which way it's going, but people like make it go backwards because what you're doing is you're sampling it with the wrong amount, and it's not going backwards, but if that's the sampling that you do, it'll appear like it's going backwards. So the next time you watch any old movies, you'll see these things where all of a sudden it's like the wagon wheel starts looking like it's going backwards. The other thing where you would see this is if on TV you watch somebody who has a very has a shirt with a lot of stripes on it.
Mm-hmm.
All of a sudden you'll see like this moire pattern come up. It'll start like looking like really. It doesn't look like stripes. It'll start looking like what's known as a moire pattern. It's like an elliptical, circular patterns. That's because the camera that they use can't resolve the high frequency stripes. So the signal that's being generated in the TV is not, that's what's known as aliasing. In fact, next time you watch TV and see somebody with a very high frequency type of shirt, watch it as they move around, you'll see that different patterns occur to that. And so just a concept that you should keep in mind when people talk about imaging or image acquisition. It's what's your sampling frequency associated with that. So sort of the demos that I'd like to show. Because a lot of people have to do this. A lot of people will throw a lot of math equations associated with this, and I'm like, what does that really mean? And this is like one of the demos that I've seen. I can't remember where I saw it, but it kind of shows you the fact that some of these concepts of how you sample a signal is very important. So that if you've got a camera now that has a certain number of pixels, you can think of each of those pixels as sampling points. But if it's not if it's not fine enough, a lot of the things that you see won't be the straight lines. It will be some straight line, going diagonal, straight again, based on one, the spacing, and also the angle that you take the image in, because that angle will introduce some aliasing because it's not fine enough to be able to sample that information. So, okay. So that's about as far as I go with Fourier transform. The one thing that and we'll talk a little bit more about this next week also, is there are equivalent techniques in what we did, and that's what's known as a convolution. And a convolution is basically taking a kernel. What is a kernel? It's nothing more than a sub-image with different weights in it. Okay. And what you do here is you basically take this, put it on top of the image, multiply it by each number, sum it up, deposit it into the middle. Move over again, sum it up, deposit it again, and you keep doing this, right? The problem with convolution is that it's slow because you're moving a kernel across. So if you have a very large image, it will take a while for you to do this processing. Okay, so just keep in mind that this would be a low pass filter equivalent. So essentially, what we did in the Fourier domain can be done similarly in the space domain by this process. You can do the same thing with sound. Instead of going into Fourier space like we did with the power spectrum, you can actually just come up with a kernel that you then go across time domain, and what it'll do is it'll smooth it out. Right? So if you think about this conceptually, in terms of sound, you're averaging. It says averaging window. What does averaging do? get rid of high frequency of big changes in your data, and that removal of big changes is basically a low pass filter. So that's why it's the concepts are the same. You're just doing the process in different domains. One you do it in frequency space. This one you do it in space for an image, or in time in a sound signal. So this is convolution, and this is actually it's something you'll hear about with convolution, deep learning, convolutional neural networks. What does that really mean? It simply means that what you've done is you've taken this information and made it smaller. This information made it smaller. And by doing that, what you're essentially doing is you're creating different versions of an image. You're creating an image at different resolutions. That's important because when you talk about neural networks and images, what you're doing is you're essentially trying to say, okay, what does this image really look like at low resolution? Because what you can start doing now is you can start understanding what the spatial extent is of different features of the image. So just keep in mind, convolutions is you're essentially changing the amount of information, and you're partitioning that. We'll talk a little bit more about convolutions next week. We'll also talk about it. Any questions with this? These are sort of those important concepts that are often thrown with a lot of math, but I kind of wanted to put it more into a conceptual point of view, so that if you are curious about the math, you sort of know where the math is going, right? Rather than throw you the math and say, okay, this is what we do with Fourier transforms. You don't need to really know about Fourier transforms, you just need to understand the concepts of Fourier transforms. Any questions about this? We'll talk a little bit more about that. For those of you who just came in, I just mentioned that I didn't get to record it, now I can get to record it, is that the computer science department actually agreed to pay for a conference at the end of June, light sound interaction here in Rochester. So Tuesday, Wednesday, Thursday, please register. You can go as your time permits to look at the different latest technology presentations in terms of imaging as well as sound. So this is actually appropriate, because what I went over in terms of sound is apropos for that. So the conference runs those 2 days. There's a lot of things that are going on. Take advantage of it. It's not often that you get the chance to go to it seems like a fairly sizable conference, so it would be cool to do that. But I told these guys, it's just go to any sessions that you want, take notes on that, and just report back. So I can give that back to the department and kind of say, okay, it was a good conference. This is those things that we want. Let's see, what else do we have? What else do I have in my Oh, so these are what are known as Macbeth color charts. They're actually miniature ones, but typically these are fairly large. For those of you who've done any photography in the old days, this is what the model would hold. They hold this, and the value of this is that it allows you. These are the color values associated with each one of these patches is well characterized, well known. Even if it's not, if it's a little bit off, one of the things that you can do for this is to actually put it in every image that you take, so that if the lighting changes, you've got something in there that does not change. You'll always know this is white, this is gray, this is black, and you can start being able to normalize your images so that you can make comparisons. This was actually brought about because I had a student who was doing where the project was to look at the plants as a function of time. They wanted to see whether the near infrared signal changed as a function of time. I said, go ahead and do it. First she started it, but then she realized she can't compare it because the light levels change as it goes through the different times of day. And I said, oh yeah, you have to put this in your image so that now when you have different lighting conditions, it is possible for you to manipulate the data so that all the patches come up with the right digital counts or red, green, and blue values for all your images. By doing that, you've calibrated the image so now you can make comparisons. So this, I'd like you to keep these with your and you can use that. Think about how you would use that in some form or not. And that's a form of calibration. In fact, that's what people do for in my field of remote sensing. What they try to do when a satellite or an aircraft flies over, first thing we try to do is actually bring some large tarp, put it on the ground, and hope that there is enough pixels from the satellite image for us to be able to characterize that. What you would typically do is if you know what that pixel or what that tarp reflectance is, then you can say, okay, at this altitude of the satellite, I know that what this should be. That means the rest of the image can be transformed to that. Caveat there is that you're assuming that the atmosphere around the rest of the image is the same, and that's where it sometimes breaks down. Is that what you have in one location, the atmosphere in one location does not necessarily match another location, but it's a start. So it's not an easy process. What else did I have? That's about all I had. I would say take the rest of the class to continue with the exercises. What we'll also be doing in the next couple of weeks. It's the third week now, isn't it? Good. Crazy. Is also get a chance for you to get the pi hat onto your machine, so you can play with that also. So the pi hat is just an addition for you to use. The reason I do that is because the pi hat that I got for part of it actually has a couple of instruments in there that's pretty useful. There's temperature, pressure, I think orientation. So you can start playing around with that. This was actually one of the components that people use to bring experiments to the space station. So this is one of the recommended ways because it allows the astronauts to be able to quickly interface with an experiment. Quickly start it, quickly run it, and also get feedback so that they don't have to plug in a keyboard and try to control your experiment. What they recommended is to actually use this interface so that it's very straightforward for them to be able to control any experiments that they may be launched up into the space station. So this gives you some sense of a process. We'll try to do that. Other activities, I'm trying to find, I've been talking to some of the people here who do imaging to give us a little field trip into their labs, targeting Wednesday. I'll get back to you guys, but we'll actually do some field trips to places around campus to see some of the imaging activities that they have. And I'm also trying to do that also for RIT, so there may be couple more class sessions where can you guys get the RIT? Does everybody have drive? Oh, I'm sorry about your car. Is your car okay? Okay, all right. I knew you had car problems. That's why I said, everybody, oh, wait a minute. Your car is not happy. So Yeah, I'm trying to get some time with the folks over at RIT to also probably do a little tour of the imaging science department, so you guys can sort of see what we do there. Put some context in some of the things I've covered, and I know that some of this stuff doesn't make sense until you actually see it in context. So, okay, let's continue. Uh, Envy, if you guys could do that exercise, and that would be useful. Just put some concepts that I went over in more concrete form. So I just posted that on general for that. Okay. I'll be back.
Nature calls.
We're running India.
I think we have to use.
This is these.
Yeah.
These. Oh, yeah. They're not specific.
Is this actually? Remind me of that.
How do we? So how do I?
Oh, no, you use, not the VNC server, you use, remote desktop, remote desktop program, yeah. You may have to, since you have a Mac, you may have to pull that from the App Store. Yeah, while you're here, you can just log into that machine if you want, but that's good practice to know how to do that.
That's all. TeamViewer?
Hmm?
TeamViewer?
I don't know if TeamViewer would do it. Remote desktop, Microsoft Remote Desktop Access. You may have, like I said, you may have to pull that out of the App Store. You might call it 5DP Remote Desktop Protocol or Program. People use it differently.
Yes, yes. So because they'll use the department credit card to distribute, so they can do that. So you don't have to do it tomorrow if you're on campus. You should go see them. So
And download data file.
So the data file, I think I might have posted some of them. Some of the data files is. For the Envy? Okay.
스페인지 어떻게 있어요?
처음 먹어요.
아니, 다운 받았는데 무슨 이렇게 있거든요. 이건
Oh, sorry, this is registration.
Yes, wanna go, tour and,
I didn't find the description.
I don't, I can find out. I actually do have, contacts. that can help.
So should we just close that and then hand that to the credit and then throw this?
Yeah.
That's
To, Jenna.
이거 하려면 그거 건강을 이거
근데 다운받은 게 이거
Yeah, I'll find out about that. I didn't go through the entire, I haven't registered yet, and I haven't gone through the registration, so that's news to me, but I'll find out, I'll see if it's worthwhile.
Do I need to do this with Jim or?
Yes, but, because they'll supply the credit.
So I need to actually submit this with her.
Yes, because she'll supply the credit card, so she'll do that, for you, so. Yeah, so that's a very eclectic, that's why that's a very eclectic group of, demonstrations, so I'm hoping that there's at least something that everybody can like, kind of, lock onto it and say, oh, that's kind of cool. I'm kind of looking forward to that.
Or one around, see what they have to say.
Exactly, no, and that's a fun thing about it. I love going to conferences, is because even though some of it may be like smoke and mirrors, because you always have a bunch of people who are like, particularly startups who are trying to like just sell people and stuff, and you kind of have to not so much leery, but kind of just like take it with a grain of salt. Then there's a lot of established folks also that will be there.
Yeah.
It'd be interesting to see what the industry's changing so fast. Might have to put any other tech industry. It's really, I have a hard time just keeping up with what the new stuff is. Always give you guys an idea of what's going on. Imaging and sound. Sound part is kind of cool too. You don't do much in it, but I suspect that later down the road, it's all gonna start right away.
Yeah, I mean, it's all signals, right?
Exactly. All signals. You gotta have to start even synchronizing stuff. Right? It's just associating it. So the trick just to.
But it seems like the techniques are working. Like they have significant implications there.
We the group that I have in our team, they've always done images. Now they realize it's like, yeah, we can't do anything with these images. You have to type like other sources of information to corroborate the imagery that you're looking at. It's kind of behind the eight ball in that respect. At least in my field, get everything from the image information. You never pull in other sources, different intelligence of the view else.
Do you know how good the imaging is on Google Earth compared to
It sounds like they might actually, I think they use Worldview 2, which is about, I can't remember what they termed, half meter, if not better. They actually broke that 1 meter barrier. There was a restriction for the longest time, but there's an open skies treaties that all the nations have for commercial satellite. There's other stuff that's higher quality, but for the commercial side, 1 meter was the limit. But I think they that got broken down not too recently. So there's people down with from satellite. I think Google Earth might actually also do airborne data for better. Yeah. And actually, the scary one is the local company right here, Eagle View, used to be Photometry. They were, I wish I could get that today. They were doing like inch resolution, and this guy, I have him come and do a lecture for my other class, and he showed one image, especially looking at stuff like, it's just his backyard. And he zooms in and sees people like playing cards. And I think you can't count it, but you know you kind of know whether it's black or. Yeah. So it was like, okay. He said the issue with that is that, like, sort of strong. You don't, it looks like you, in order for you to cover something.
Yeah, you have to go over, you're able to do so.
Exactly. That's always been the case, and and I think a lot of people who aren't aware of the technology have this like unrealistic expectation that the entire world is at that resolution. But I think that's the goal. That's the goal. Like, you can't say that it won't happen because I would 10 years ago I would have said you're crazy if you can have the world on your phone. That still blows me away to be honest. It's like nuts. The GPS accuracy is just crazy.
Have you seen, so, tree program?
No, not all. This is the
I've seen super high res.
Yeah, no, I wouldn't be surprised. What actually, before this guy, before these guys were doing it, there was about, I wonder if it was one of the national labs. What they basically did is like, got a whole bunch of like, regular something such as, like, put it together. And came up with a larger. So they probably have a better system than that, but that was the first time I saw like basically a gigapixel image, and what they did in that situation is to go off the shelf type of components and start putting what they're getting. But nowadays it's like, that's crazy. That's crazy. It's nuts. It's nuts. It's a crazy world. No, I've never seen that one. No. Crazy. No, and like I said, it's so hard for me to keep track of. Usually they just monitor a few sites. Spend, usually they spend your entire day just going through all the different rabbit holes of technology.
It's supposed to be on 195.
Wow. That's that's and that's part of the issue also with data. It's data management. Yeah. There's a lot of companies that are just trying to get the infrastructure in place.
And there's, I can ask Chris,
Okay.
and maybe they would send me like a super copy.
No, they stopped doing that. It's kind of sad. I think they stopped doing that. You can try again. I still tell people always check because a lot of these companies change their policies and increase the charge. Some companies will also be things with academics and change. You always know this because the CEO. So Eagle View, the one I was talking about, when they had the high resolution, the guy used to always come to my class to give a demo, talk about about the company, and then all of a sudden, he's like, I can't do it anymore. It's management. He's pretty short-sighted. I don't think that's kind of sad because I have the opportunity to tell people about the company so that when they go out, be customers, but he said management. Yeah,
too short-sighted with the bottom line.
Your time's more valuable. Like one to talk to people in academia.
Yeah, I have a signature, so. Another form.
So with these tutorials, you want us to like take screenshots or something, or just
If you want, because I think that would be helpful for you to sort of go back in the future to kind of understand that, so it's useful for you to do that.
what's the shortcut for screenshots on Windows?
Oh, I'm gonna never forget. It's Windows Shift S for that one. Did that work?
Yeah.
But I thought I would. The problem is I work across all different OSs, and it's such a thing that drives me crazy is the control and the
Yeah, really.
control and the whatever Apple Clover Leaf, whatever they have there. Drives me. I've lost so much text because of that. Copying something and it's character and based on that text.
Have a good weekend.
And they should have some of these labs outside.
It's such a nice day. Okay.
Like we're walking over here, like, oh my god, this is a beautiful day. The weekend supposed to be. What's the weekend supposed to be like? Right now.
Could be a nice weekend for sure.
Oh yeah, no. Well, it's nice. Saturday's nice. Monday, 100% rain.
No, it's better than the weekend. So what festival is this weekend? I don't know. They always have a festival every weekend.
Lab reports for 3 and 4 and the project statements each one.
I think I need to update that, but if you can get those in, that's pretty flexible with the stuff and stuff.
Thank you.
You're welcome.
I have a couple of ideas for projects I'd like to work on.
Okay.
But I haven't done them before, so I don't know if I can do them. So I'm a little bit worried about biting off.
No, and then that's fine. I think I'm very open to trying. Oh, you okay? At least you didn't bang your head this time. No, I'm very much open. Yeah, I'm very much open to that because I don't want to say that the failure is I encourage failure, but I encourage exploration, and if it doesn't work out, it doesn't work out. I mean, I think it's a data point for you of knowing what that was, and so if it's something that you really care about, I think that's more important that you explore that. So I figured it's steganography that you're looking at.
That was one of the things I was looking at.
Yeah.
But I don't know. I mean, it's doing simple stenography is trivially easy.
Yeah.
Doing complicated stenography, like making it undetectable, is probably requires a course.
Yeah, no, and I guess here's my recommendation that would help me out is maybe even just
based on some of the tools that we've talked about,
Mhm.
consider coming up with a tutorial for that. And because I know very little about it, and if you can contribute to basically coming up with class material, I'm open to that.
Oh, okay.
I mean, try to push it a little bit, but that's the kind of stuff that I like looking through. Somebody having an example, I'd look through. It's like some of the stuff that I've sort of presented here is stuff that I've seen previous students generate, and to me, like if somebody comes up with a tutorial on a concept that is new to me and to most people, I think that's a good way. If we could incorporate some of the tools and techniques that we talked about, I'm open to that.
Yes.
I think that's
Well, I think I definitely do that.
yeah. Okay, so let's make that your like baseline, and then anything above that is gravy as far as you're concerned. Think about that in terms of that level of.
So I was also thinking of another project I was thinking of trying to do was trying to taking a picture of text and then trying to identify letters and stuff like that in the text.
So that's
Using different people's handwriting, which is a lot harder.
yeah, and that's actually, let me think about that. There is a data set, and I'm trying to think if it might be of use. There's the MNIST data set is what people always use in deep learning. It's an example of character recognition, and I'll post that on the Slack channel because that's sort of the standard that people always do with deep learning. Maybe if you go look at that, that might give you some insight as to whether you want to use a different technique or just compare. I mean, again,
Well, so the trick is I haven't actually I've done a lot of work just on my own with AI stuff because I think it's interesting, but I haven't actually formally gone through the course. So my understanding of it is limited.
yeah, and again, exploration is what I always encourage people to do. You can somehow merge it into something that you're very interested in. Me telling you that you should do this is not as effective as you saying, I really like this. I care about this problem and address that. So just give us an opportunity. I use this class as an opportunity to do exploration. I think people learn a lot better when they care about the problem. Yeah, I'm the same way. If I don't care about the problem, but somebody telling me that you gotta get this done.
Yeah.
It's a little stressful, but it's like I don't enjoy it, and it's something I kind of want people to sort of a little bit of a breather from the stress of semester system. And granted, we're doing this in 6 weeks.
Right.
To me, it's unrealistic to think that you're going to like grind through all that stuff in a reasonable manner and have the retention that you typically would do on a 20-week semester situation. So that's why I emphasize more on the documentation side because
So you can actually go back and
exactly the reference. And sometimes it's like in that amount of time, you sometimes don't appreciate the application. It's like, okay, I kind of get that you said that you would use it in this scenario, but I don't necessarily see it right away. Maybe later people say, oh, I remember that. Go back and at least you have the material. Because my experience sometimes is when you Google some things, I mean, you just come back with it's so much. There's so much that sometimes you want something that kind of walks you through a small set of steps that you can absorb. That's it's always been I don't say I long for the days when you didn't have Google because you were kind of like forced to like really look through for things.
Yeah.
But at the same time, I do appreciate Google
but the amount of information sometimes can be daunting.
Well,
What
and
you
the
get.
trick is always finding the information at the right resolution that you need it.
Yeah, and then the quality also, because sometimes you get like, you spend a lot of time just going through low quality information and trying to find the needle in the haystack or a couple of needles in the haystack that says this is the technique you want. So if it's a Stack Overflow, I say yeah. Well, cut and paste that, baby.
Hopefully it doesn't destroy my computer. Did you ever get a chance to watch that video I posted?
No, I did not. I'm gonna write that on the list because I'm taking the day off tomorrow from my work. So was that the satellite
Yeah.
downlink? Yeah.
I mean, I can spoil the video for you. Until
No, don't.
Well, I wanted to ask you if I wrote up a proposal for an independent study with that for like the second summer session, would that be something you'd be interested in?
Yeah, I mean, if it has to do with satellites, yeah, I'm always.
I mean,
And then if it's something that I'm going to learn something from you, definitely.
well, you won't learn it from me. We'll learn it together.
Well, no, and then that's I do my best work, or students do their best work when I work with them because it is, to me, it is a collaborative thing. I'll